I remind you that last time we introduced a deformation of the Ruijsenaerts-Schneider model, and equations of motion are as follows. This part is the same as in the Ruijsenaerts-Schneider model. And there is additional term. Where ui of x is the following function. It is important to note the following identity. And from this identity, we can observe the first integral of motion, which is just sum of velocities. You should add all equations to take the sum over I, and then this part cancels because this function inside the sum is antisymmetric. And because of this identity, this term also vanishes. Today, we will discuss the commutation representation of this model. Let us introduce such matrices. This is a kind of Lax matrix. However, it does not obey any equation of the Lax form. But in the case when G equals to 0, it becomes the Lax matrix of the Ruijsenaerts-Schneider model. This part is like in the Ruijsenaerts-Schneider case, and there is additional term. There are two spectral parameters, k and lambda. And there is also matrix R. It is convenient to fix G equal to sigma of 2 eta. Because if G is non-zero, then you can put there any value by rescaling of the time. And the equations of motion are equivalent to the following relation for these matrices. It is also instructive to introduce two matrices, M plus minus, here minus, and then you don't need the matrix R, and this commutation relation can be written, introduce also L of k lambda equal to that L minus k times identity matrix. And then this commutation relation is equivalent to the following. If M minus was equal to M plus, this was the Lux equation, but now they are different, and this relation of this kind is called Monakov's triple. The calculation necessary, which is necessary to prove this statement, is non-trivial. It is rather long and complicated calculation, which uses some non-trivial identities for elliptic functions. I don't want to make it now on the blackboard because it requires a lot of long formulas. But in the lecture notes, which will appear on the site, this calculation will be presented. The key step in this calculation is to prove the following identity with those matrices. This is Monakov's triple, but in the identity you obtain here some additional matrix P, which is equal to the following. X is diagonal matrix with coordinates on the diagonal, and we will also need some matrices Z plus and Z minus, also diagonal. Plus G times U minus minus U plus, where U plus minus is the diagonal matrix which with UIs on the diagonal. And here is some matrix A. This matrix is diagonal. Z plus minus is diagonal matrix of this form. And A is the following matrix. Now everything is defined, and the requirement that P equals 0 means that all diagonal elements of this matrix are 0. And this is exactly the equation of motion. If you equate to 0 every diagonal element. So the problem is to prove this matrix identity. And as I said, this requires some non-trivial calculations. Now, what is there is important corollary of the Monakov's representation, and it makes it possible to derive integrals of motion. Although the evolution is not isospectral now, the determinant of this matrix L conserves for any k and lambda. It looks like a characteristic polynomial of the matrix L, but now it is not a polynomial because k enters not only here, but also there is k inside the matrix L. So this is not a polynomial, it is a Laurent polynomial with positive and negative powers of k. And it is easy to prove that time derivative of this determinant is 0. So it is a conserved quantity. Let us apply the derivative to the logarithm of this determinant. Then it is derivative of trace of logarithm, which is trace of derivative of L times this matrix to the -1 degree. But the Monakov's representation states that this is trace of R. But as I said, trace of the matrix R is 0. So this quantity is conserved. To find the spectral curve, it is convenient to renormalize the L matrix in the following way. Where G is diagonal matrix with this matrix elements. And also let us introduce another spectral parameter Z, which is related to K in this way. Then the equation of the spectral curve can be written in the following form. And L tilde here is the following matrix. Here, phi is the function of this form. Let us divide this by sigma of 2n eta minus lambda and denote this by q. The determinant can be calculated explicitly. In the Rosenard-Schneider case, when G was 0, it was a rather simple calculation because this matrix and any diagonal minor of it is Cauchy, elliptic Cauchy matrix multiplied by diagonal matrix from the left. And determinants of Cauchy matrix is known. We already discussed it. But here, the situation is much more complicated because we have a sum of two terms. Each term is a Cauchy-like matrix multiplied by some diagonal matrix, but to find determinant, you need to consider determinant of a sum of two matrices. And this is not so easy to deal with because the formula for determinant of sum of two matrices, say A plus B, is the sum of determinants in which some columns of the matrix A are substituted by the corresponding columns of matrix B. And the sum goes over all such possibilities to substitute some columns of the matrix A by columns of the matrix B. Nevertheless, this calculation is possible to do. And again, I don't want to show it explicitly in the Blackboard. You can find it in lecture notes. And the result is the following. For Q. It is a Laurent polynomial in Z. These coefficients are integrals of motion. They can be found in explicit form, which I will show you a bit later. And there is also a polynomial in inverse powers of Z. And here we have the same coefficients. And the result for the integrals of motion is as follows. This integral Gn is the integer part of n over 2, so when n is depends on parity of n. here. Coefficients G and N. And the formula for them is as follows. The sum goes over subsets of the set of numbers from 1 to n, such that they don't intersect. And the number of elements in I is m, and the number of elements in I prime is n minus 2m. Let me call this set by n. And the functions which enter this expression are as follows. This is a rather complicated formula, but explicit. And let me show two examples, simple examples. J1 is just sum over all velocities. And J2 is as follows. This part is the same as in the Rosenart-Schneider model, and there is additional term specific for the deformed model. In fact, one can prove that these two terms are equal. So I write it in this form just for symmetry between plus and minus. And also in this identity that these two terms are equal is a particular case of a more complicated identity, which are useful for calculations. And this identity can be written in this way. Here n prime is any subset of n. And this identity that these two terms are equal is a very particular case of this one, of this general identity. The simplest, first non-trivial case. In fact, in calculations related to this model, the derivatives of this identity in these variables are also used. So the corresponding identities which follow from this one are already of very, they are very long and complicated. This is all about Kalodjera-Moser and Rosenard-Schneider models. And now we will discuss their spin generalizations. In all models which we considered before, the particles did not carry any internal degrees of freedom. They were just scalar particles, but it turns out that it is possible to introduce, to associate with each particle some internal degrees of freedom, which are described by matrices or vectors connected with each particle. And in the evolution of the system, these internal variables are also, they also depend on time. time. And the equations of motion is a system which connects dynamics of coordinates with dynamics of spin variables. The spin generalization of Calogero-Moser model, these internal degrees of freedom are usually called spins by analogy with quantum mechanics. Spin Calogero-Moser models were introduced by Gibbons and Hermsen in 1984. Let ith particle with coordinate xi be associated with a variable, spin variable Si, which is a matrix of some size n times n with matrix elements S alpha beta and the indices corresponding to this internal degrees of freedom will be denoted by Greek indices. So alpha beta run from 1 to n small. And the Poisson brackets for these variables are given by the following formula. They are zero for different particles when I is not equal to j, and when I equals j, the Poisson bracket is as follows. This relation is the same as the relation for generators of GLN algebra. If you replace Poisson brackets by commutator, then these SIs are generators of the of this Lie algebra. And in terms of these variables, the Hamiltonian can be written in the following form. This is the kinetic term, which is the same as for the scalar model, and the interaction term contains spin degrees of freedom. Here we have trace of Si times Sj times Weierstrass function. We consider the most general elliptic case from the very beginning. The Hamiltonian equations which follow from this Hamiltonian can be written, can be easily derived, and they have the following form. Here is the commutator of matrices Si and Sj, Weierstrass function, and the equation for coordinates is of the form this is a system. From the first equation, when you sum over all over all indices, you immediately conclude that this trace of each Si is integral of motion. I said a wrong thing. You shouldn't sum over I. You should just take trace of both sides of the first equation. Then on the right-hand side, you have trace of commutator, which is 0. So this is an integral of motion, and it is convenient to fix values of these integrals of motion by putting this trace equal to 1 for each particle. All particles are identical, so we should these integrals of motion should be equal for all particles, and it is convenient to put them equal to 1. In fact, it doesn't matter because this if you put here any constant, it can be by rescaling. You can always, without any loss of generality, to fix it to be 1. However, for matrices Si of arbitrary rank, in particular for non-degenerate matrices Si, this model is not integrable. It is integrable only in the case when rank of each spin matrix is 1. So they are very degenerate matrices. And in this case, it is convenient to parameterize them by two vectors. So to say that S alpha beta is a product of A alpha times B beta. Rank of such matrix is exactly 1, and now the dynamics becomes dynamics of these vectors A and B as functions of time. And these Poisson brackets for S matrices are equivalent to the following Poisson brackets for the vectors A and B. So they are canonical variables. And for A's and for B's, all Poisson brackets are 0. So they are really canonical variables like P and Q. And then, in terms of these vectors, the Hamiltonian acquires the following form. it is convenient to assume that when you see two repeated Greek indices, you should take sum over them from 1 to n small. So here is a double sum over mu and over nu. And the Hamiltonian equations of motion take the usual form. And it is easy to write them explicitly. The condition that trace S is 1 is then equivalent to the condition that the scalar product of these vectors A, B for each particle equals 1. This model has the Lux representation. And the Lux matrix is as follows. It depends on a spectral parameter lambda. And here we have scalar product of vectors B and A for A and J particles times Lamé Hermite function. prime means derivative of this function with respect to the first variable. And the problem for you is to prove that the Lax equation with these matrices is equivalent to the equations of motion. As usual, we can introduce higher integrals of motion as traces of the Lax matrix. In particular, H2 is that Hamiltonian H plus constant. Each Hamiltonian, each higher Hamiltonian generates its own Hamiltonian flow, and the corresponding time of this flow will be denoted as Tk. And another problem is to show that the quantity G alpha beta, this matrix which is the sum over all particles of S alpha beta, or in terms of the vectors, it is this, and the problem is to prove that these quantities are conserved for each Hamiltonian flow. Okay. Later, we will see that this dynamics of the spin generalization of the Kalodger-Moser model is the same as dynamics of poles and coefficients in front of poles in the for elliptic solutions to the matrix Kadamtsov-Petriashvili hierarchy. Matrix, the Kadamtsov-Petriashvili hierarchy has generalization to matrix form, in which the dependent variables become matrices of size n by n. So if we consider a solution, then and assume that it has a pole at some point in the complex plane, there is also a coefficient between this singular term, and in the scalar Kadamtsov-Petriashvili hierarchy, this coefficient is fixed, but in the matrix case, it becomes a dynamical variable. And it can be shown that the matrix, which is this coefficient, is of rank 1. So it can be parameterized by two vectors, like we have here. And the corresponding dynamics with respect to Kadamtsov-Petriashvili times is the same as this spin Kalodger-Moser dynamics. The Rosenard-Schneider model also has spin generalization. However, in the most general elliptic case, the Hamiltonian structure is not known. This model was introduced in 1995, but since that time, the Hamiltonian structure still is not known. This is a problem. In rational and trigonometric cases, which are obtained as degenerations of this general elliptic case, something is known. At least in rational case, the Hamiltonian structure is known, but it is rather complicated and not clear how to generalize it to trigonometric and elliptic cases. So we will start from equations of motion, which were obtained in our joint work with Krichyver. From dynamics of singular solutions to Toda lattice hierarchy. Again, we have in variables xi, xi dot. Already we don't have momenta because we don't know what they are, what is the canonical pair of momenta, and vectors A and B. And the equations of motion are of this form. From these equations, you can see that xi dot minus bi times ai, scalar product, is conserved. It is an integral of motion. It is convenient to fix them by putting xi dot equal to this scalar product. In the Kalodjera-Moser model, this scalar product was fixed to be 1. But here, in the Rosenard-Schneider case, it is not 1, but equals to xi dot. This model has Lax representation with the following matrices. This term is actually not important because it is proportional to unity matrix. And again, the problem is to show that the Lax equation is equivalent to these equations of motion. The integrals of motion again can be taken as traces of powers of Lax matrix or as coefficients of the characteristic polynomial. This equation defines a complex curve. It is called spectral curve. Some properties. This curve is more complicated than the spectral curve in the scalar case, but nevertheless, some properties of it can be found. In particular, the genus can be found. I don't have the formula at hand. It depends on the number of particles and of the size of the number of internal degrees of freedom. Okay, so it remains about 10 minutes, so we have time to pass to another topic. This is almost all what I planned to say about many-body systems, integrable. And now we pass to the second half of this course, namely to derivation of all this integrable dynamics of the many-body systems from integrable hierarchies of partial differential equations, differential and difference. And these many-body systems will be obtained as dynamical systems for poles of singular solutions to such hierarchies like Kadamtsov-Petviashvili or Toda. And let me start from Kadamtsov-Petviashvili hierarchy. We begin with the simplest equation, which is called Kadamtsov-Petviashvili equation. It is an equation for a function of 3 variables of the following form. if u does not depend on y, you get Korteweg-de Vries equation in two variables. And this is Kp equation. It is the first simplest member of the whole infinite hierarchy of differential equations which are compatible with this. And we introduce the hierarchy a bit later, maybe next time, but today we will consider this equation. It has a commutation representation, which is a key property for integrability. Introduce the following differential operators. Second order operator and third order operator. The problem is to show that the following condition implies the Kadamtsov-Petriashvili equation. When we take time derivative of an operator, this means that we differentiate its coefficients. In this case, this is just derivative of u. And here we have the derivative of this term is 0 because this is constant. And we have derivatives of this and this. U and v are some functions of the three variables, x, y, and t. The variables x and y are usually interpreted as space variables in two-dimensional space, and t is time. This condition is sometimes called Zakharov-Shabat equation. Or zero curvature condition. In fact, it looks like an overdetermined system because the highest order of the differential operator, which is in the left-hand side, is probably 4, because the highest derivative is 5 when this is multiplied by this, but it cancels, obviously cancels, because the coefficient is constant, so the derivatives are 0, and in the commutator of these terms is also 0. So the next possible degree is 4. So we have degrees 4, 3, 2, 1, and 0. And the coefficients in front of each degree should be 0. It turns out, if you do this calculation, that these coefficients vanish identically, and you are left with two equations obtained by condition that the coefficients between first and 0th power of the derivative are 0. And this is a system of two equations for two functions, u and w. From this system, you can exclude w and obtain a single equation for u. And this is just the Kadamtsov-Petriashvili equation. This condition, the Zakharov-Shabat equation, is a compatibility condition for the following linear system. For some function psi, which depends on the space and time variables, and also on an additional variable z, which is called spectral parameter. So this spectral parameter doesn't enter this equation, but the solutions are parameterized by additional parameter, which is hidden here. This is first equation. The second is a similar one for A3. So this is a system which is overdetermined in the compatibility condition, which means existence of a family of solutions, is just this Zakharov-Shabat equation. The simplest solution is when u and w are 0, then psi is just can be taken as in the following form. When this u and w are not 0, we have a series in inverse powers of z with some coefficients. And the main idea which makes it possible to solve, to find large families of solutions to the Karamazov-Petriashvili equation is to solve first this system for psi, which is easier because this system is linear. And then it can be by substitution of this series into this equation, you can find that u as a function of x, I, and t is minus psi 1, which is the first coefficient in the wave function. So if you manage to find a solution to the linear system, then you immediately get, looking at this first coefficient, you immediately get some function u, which is a solution to the Karamazov-Petriashvili equation. And this is the idea of the general method of solving nonlinear integrable equations. Another problem is to show that the substitution so if u is represented as second logarithmic derivative of some function tau, which is called tau function, which is a very important object in the theory, then the Karamazov-Petriashvili equation can be represented in the form which is bilinear in tau. And the last thing which I would like to say today is the following explicit solution for u, which is called one soliton solution. it depends on two parameters, P, which are usually called P and Q. And the explicit formula is like this. You see that this solution has a singularity in complex plane. So there is one second order pole. When you consider this as a function of x, it has it is a periodic in imaginary direction, and you can choose a fundamental domain. And there is exactly one pole in the fundamental domain at some, this pole is of second order, and the position of this pole depends on the other two variables, y and t. And this is the simplest example of dynamics of poles. In fact, the Kadamov-Saakashvili equation has more general n-soliton solutions. They are characterized by a larger set of parameters like this P and Q. And correspondingly, they have more singularities, more poles in the fundamental domain. And these poles move somehow, poles in X. They move somehow as functions of y and t, and we will see that this dynamics is exactly like Kalodjera-Moser dynamics. In this case, trigonometric. So next time we will consider rational solutions of KP equation, and then pass to trigonometric and elliptic. And for today, this is all.